Yeah. Okay. Hi, everyone. Hi, Joe. Thanks for the invitation. It's great to be here again. Today I'm gonna talk about some new technical results, some from yesterday. I think they at least potentially pose a serious problem for the new firewall arguments of Busseau, Merelf, and Paczynski. I haven't, plugged all of the holes yet. So I'll prove some theorems which are true, and then we can try to interpret whether or not they indeed pose a problem for the argument. I myself am not sure, so I welcome questions and discussion. I should just partially apologize. So in order to get through the proofs in a way that is understandable, I have to aim this talk. It's going to be a little bit technical. If I started at the beginning and tried to philosophize everything, I never get to the actual stuff. But as a bonus for people who maybe are sort of more casually interested, I'll throw in a proof of Page's theorem in the middle. That'll be like 2 lines. Using the technology, it's pretty easy. So if you want to see, if you don't even know about Page's theorem, then I'm afraid I have nothing for you. But it's okay. So what I'm going to do is, I'll review the new firewall argument, and then I won't write the outline. I'll just go and. Okay. Well, I'll tell you. How about this? I'll say the outline. I'll review the argument, then I'll make some comments about that maybe suggest a possible issue, and then I'll prove some theorems. Okay. So I should say that, so the original information loss argument from Hawking, and then the later refinements by Samir, and then by Amps this past year. Yes, Lenny. Yeah. So good. So the sort of now the old information loss, Mather, Amps kind of arguments are formulated to apply to any particular black hole microstate. Okay. But the new argument is based on being applied to an ensemble of states and talking about sort of the typical behavior of states in that ensemble. So it has a slightly different flavor. I should maybe briefly comment that the old versions, the ones that are applied to sort of black hole by black hole, I think basically they've stood up. But I think, at least there's one set of ideas which I won't review, but I'll just mention, which you can think of as strong complementarity plus computational complexity, which I think have held up against those arguments. That's something we can debate, but this talk is not designed to debate that. And then you can try and extend that into, embedded into what various people call A equals RB or ER equals EPR or whatever. But that introduces new problems, and so far it's unclear that those can be resolved. I think the new problems I think are nicely discussed in the Ampsys paper, and then in Raphael's new paper on frozen vacuum. I want to focus today on the new firewall argument. So what's the claim? And I should say, the reason I want to focus on it is because, at least from my point of view, this one seems to get around the strong complementarity plus complexity argument. So that's bad for me, or I don't know, for me or for us or whoever. So I want to see if I can drill some holes in it. Okay. So basically the way the argument works, I'll give you one version of it. So I'll draw a Minkowski black hole, but whenever you're worried, you can put it into ADS in your head. You think about someone who falls in. And the black hole is formed down here. Maybe I'll make the formation process orange, some extended formation process. And the idea is to use a basis of initial states which have some sort of pathological property from the point of view of somebody near the black hole. So what was suggested by these guys in their papers is to use sort of product states where either the zone or some part of the zone is pure by itself. And then the claim is that there's a complete basis of such states. And then, moreover, the claim is that, well, roughly because, yeah.
Are you asserting that when you run that state back, that it's going to look like collapse?
No, I'm allowing collapse in the generalized sense of, building things up slowly over the page time or over exponential time in ADS. Yeah, that's why I didn't draw it like that. I sort of drew it like some sort of extended. But I should emphasize, and this is what was emphasized especially by Joe and Don, that this all still fits inside this guy's light cone. So you can't just, you can't throw out the full set of possible initial states by saying I just want to stay in a diamond. The full Hilbert space has to be embedded into strong complementarity. So now the claim is that you can find a complete basis of these states where, like I said, so say you pick some mode in the zone here, and then you pick a basis where this is pure by itself. And then, well, there's various ways to say the argument. So first of all, they claim that
Daniel, I'm still confused. Is this place inside the collapsing matter?
Sorry, no, it's here. Yeah, say you cross here. Yeah, sorry. So then the claim is that you can, you can factorize the Hilbert space here right into the zone, and then you can choose a basis where it's pure. And moreover, there's a claim that you can do that and stay in the microcanonical ensemble. Okay, there's a claim that you can, if you work in the space of black holes of fixed energy, that even of that subspace of the whole Hilbert space, you can find a basis which is, well, the way you set it, product, but I think we all agree that order 1 deviations from thermality is enough. If you can find a basis where there's order 1 deviations from thermality, then you can get into trouble. Let me say a little bit what the trouble is. So I guess the way that I would say it is that if you can find a complete basis of the microcanonical ensemble where the states are bad, then you can, the microcanonical ensemble is just the identity density matrix which will be diagonal also in that basis. So you can just say it's a classical probability distribution of states, each of which is bad. So then, okay, fine, they're all bad. You don't know which one it happens to be, but tough luck for you, right? Okay, so that's the argument. That is one way of saying the argument.
And just to refine this, you don't have to use the exact microcanonical ensemble. You could use some slight but controlled deviation from it.
That's right. Yeah. So the actual microcanonical ensemble has some width, right? So then you can play with the width a little bit, or you can consider massaging things a little bit. That's right. So the point I'm going to try and emphasize, though, is that indeed you are picking the subspace out of a larger space, and it's not a priori obvious that indeed you can find pathological states in that subspace. So I'm going to quantify that mathematical problem today. But let me just suggest two possible issues that suggest that this may be an issue.
Okay, just before you go on to this other solution, you agree that if if your interior operators depend on the state, then this is not a problem. So good. So that's why I wanted to use, in strong complementarity, you imagine that conventional quantum mechanics applies in a single causal diamond. So the people who want to have state-dependent operators, or at least some subset of them, want to say that the state dependence is only in the map between different diamonds, and that if you stick to one diamond, then you're allowed to use linear operators. So I'm going to insist on that, following the assumptions that these guys make. But I think it's reasonable. I'd rather not have observable violations of quantum mechanics in a single diamond. Okay. We can.
But I think, let me leave it at that. Okay, so first of all, it's sort of obvious that the microcanonical ensemble can't really be treated as a product between the zone and the horizon, because say here's the horizon, and here's the zone, which I'll call B. You can, by fiddling around with the zone, you can clearly make a bigger black hole, right? So it's clear that it's not actually a product state. And the actual Hilbert space, which really contains sort of arbitrary manipulations of both of these, is some guy whose entropy is actually the original entropy plus some delta S, where delta S is of order S. Okay, that's the sort of zeroth order bound on how much bigger the Hilbert space has to be. And then now we can try and play the game of shrinking this delta S. Okay, and that's a problem which I haven't completely satisfied myself. Good. So the modes in the zone, say, are confined to R less than 3m, let's say. Okay. So let's say delta. So let's say that you could imagine a black hole whose Schwarzschild radius is 3m instead of 2m, a bigger black hole, and then that would give you a shift in the entropy, which is proportional to the original entropy. Okay. So that's an upper bound on how much bigger the Hilbert space is if you allow arbitrary manipulations of the zone. Okay, I'm not claiming that this is the lowest upper bound, but well, good. So that's a question, though, right? So clearly, if I take the whole zone and I'm allowed to do whatever I want, start exciting quanta, then eventually I will make a bigger black hole, right? So you somehow have to fix the energy or have some kind of
But you could also say that, by the same right, I can just increase the energy by manipulating degrees of freedom very far away and throwing them into the black hole.
Yeah. So
it was very important to distinguish between the mineable zone and the zone.
No, but I'm talking here about the modes whose energy is of order the temperature. I'm not talking, the guys that are important, that we really think of as being sort of the things that the firewall would be made out of. I'm not talking about, I don't know, you have a baseball here. That is not what I'm talking about.
Talking about increasing the population of those modes?
Well, that's one thing that you could do.
I mean, you're certainly the entropy in the thermal atmosphere of the black hole, as normally described, outside some reasonable non-Planck scale cutoff, is certainly much less than the entropy of the black hole.
Well, they both scale like the area, though, right? That's all I meant by this.
Oh, that's what you meant.
That's what I meant. Yeah, sorry, I meant that just they scales like the area.
Oh.
Yeah. Yeah. Yeah, I'm not sure, right? I mean, I think if you allow yourself to isn't it true that, so say I start exciting these modes, right? I mean...
well, let's not excite them. Let's just compute the entropy contained in the Rindler vacuum, right, or in the Unruh vacuum.
Yeah, well, right, then there's this question of, so when I think about entropy, I'm thinking of entropy of formation, right? So I mean, the thing that's supposed to be e to the a over 4 is the number of different ways that you can make the black hole, right?
Sorry.
I mean, this isn't going to be too important.
Is your point?
Yeah.
I mean, let's agree that the full entropy is just S with no corrections. But now you want to do something more by identifying some tensor factor in the Hilbert space.
Well, yeah. So we're trying. I mean, the space.
That is an entropy in a larger Hilbert space. And now there's this game of sort of dividing the Hilbert space into tensor factors and saying that one of them is the one that carries the entropy. Is that the?
Yeah, I'm just trying to say that when you want to do this factorization into the zone times the horizon, you do that at the cost of having the Hilbert space be a little bit bigger. That's all I'm trying to say. And I was just trying to give a picture where, at least if you allow arbitrary manipulation of the zone, then it's obvious. Now, of course, you want to conserve energy because you want, so you don't, I mean, clearly if you just start putting stuff in here, then you're going to be able to do lots of things.
Excuse me, Daniel, but in a ordinary thermodynamic system, such as black body radiation in a cavity, I could ask whether I can separate the Hilbert space of the left.
I'm about to talk about that.
Let me just connect this to this point that you're making. I could worry about the left and right half of the cavity, and I think we probably agree that you can, to a good approximation.
I know, but I'm about to say why that I think it might not be true here. So.
Okay, but this already disagrees with how we would treat that case.
Yes, I agree, and I'm going to say why.
We would not say that all these short distance degrees of freedom are somehow part of the entropy that we have to worry about when we do.
But I mean, you agree that the Hilbert space is larger, okay? I mean, you can't disagree that the microcanonical ensemble is a subspace of a larger space, and moreover that the factorization of these two doesn't have to respect that. It's a matter of principle. There's a question of, I mean, approximately it might respect it, and that's what I want to get at, but it's only approximate, okay? Now, let me just make one more comment before I'm going to say something which is mathematically true. So I said this is the part which I haven't completely sorted everything out to my satisfaction. But let me just make the other comment here. So Indeed, so if we think about a gas, and we imagine dividing it into two pieces, then it's true that when we talk about the microcanonical ensemble, we tend to ignore the interactions that come from the interface here. And the reason why we do that is because the energy of these interactions scales like the area, whereas these guys scale like the volume. So we're allowed to neglect the interactions by something like L thermal over the size of the box. Okay, that's what allows us to neglect the interactions and say that the energy here is E left plus E right. Okay. Now, when you think about these Rindler modes whose energy is of order the temperature, then their proper distance to the stretched horizon is always of order their wavelength. Okay, so to some extent, you can't really think, at least it's not clear to me, that you can ignore the interactions between the stretched horizon and these modes. I don't have a completely solid argument that you can't, but at least I don't see a completely solid argument that you're allowed to ignore it either. Okay?
Well, it's just the geometry. The geometry of the zone is sort of hyperbolic. And,
that's right. That's right. So that's a problem about the modes, which I think needs to be quantified more.
Well,
yeah.
Do you think that this is an issue which can, in principle, be studied using effective field theory, or is this some issue that transcends? Are you supposing this is some issue that transcends effective field theory and can't be calculated?
Yeah, I'm a little agnostic about it. I certainly feel like effective field theory has not been exhausted in trying to understand this, to what extent this is an issue, but I haven't gotten it all through my head yet. Yeah. You mean the Rindler energy? Yeah, but, well... Yeah.
Aren't you just saying the coupling energy between the zone and let's call it the stretched horizon is always the coupling energy is always proportional to the area, but all of the energies are proportional to the area?
Yeah, that's kind of what it seems to me should be the case.
Well, that's clearly true.
Yeah. I mean, I'd like to quantify it better. So before I declare victory here, I need to admit that I haven't understood this in detail. I'm just saying that it seems to me that there's at least some issue here. Yeah. Yes. That's right. That's right, but you can try and beat that by doing what Joe and Don do, which is looking at trying to isolate some particular mode that's sort of safely away from the stretched horizon. And it's unclear to me to what extent that really helps, but that's sort of a quantitative thing.
But Dan, so you're taking modes that are ordinarily not excited and assuming...
no, I'm not. No, I'm only talking about modes whose energy is order of the temperature.
Can I finish?
Okay.
You're assuming, I think, that they can be excited all the way up to some cutoff in order to count this large number of states proportional.
No, sorry, these modes are excited, right? I mean, the ones whose energy is of order the temperature are excited. They're Rindler modes.
Well, they're in a definite state that's correlated with the stuff inside in the usual field theory.
Well, I don't want to assume about the interior. I mean, there's some physics that we don't understand going on at the stretched horizon. There's some sort of dynamics there, which I at least have not, made myself happy with.
If you take the large M limit, then it is Minkowski space, and there's the usual Rindler story versus Minkowski space. And
but this whole conference is about how we know that you're not allowed to trust that. Okay.
Well, the question is where we deviate from that.
Right. So this will be the end of the fluffy part of the talk. The motivation is just to say here that there is at least, it's possible that in trying to factorize, you have to go to a larger Hilbert space. That's the only message that I wanted to convey, and now I'll study that problem quantitatively using quantum information theory. Okay, and now I'll say things which I know are true. So from now on, only technical questions. Okay?
So I'll better get this one in right now.
Please.
First of all, you need to adjust your microphone. It's rubbing against something.
Oh, I'm sorry.
Secondly, so it's true that you don't get growth like the volume, but you do. What you can do is you can fix the number you can fix the L up to which you want to create. Establish a firewall. Mm-hmm. And then take the limit where the Schwarzschild radius goes to infinity.
I understand.
And in that way create,
So I've thought about that. I mean, I don't think it really helps.
Well, okay, I think it does. Also, in that limit, what happens is that the modes in question have larger and larger wavelength at the edge of the zone. And so you're making a smaller and smaller error by excluding the very short distance, the stretched horizon region over which there are interactions.
So, Rafael, what you're going to see, and I hate to spoil the punchline, but I'm afraid it's the only way to continue, is that the shift in entropy needs to be almost nothing to obliterate this argument, okay? So, I mean, I'm not talking about small, I'm not saying, oh, the delta, I don't need delta S order S, okay? In fact, I'm just going to need it to be order 1, okay? So, and I don't think that you're going, I simply don't think that the approximation that it factorizes is correct at that level of accuracy. Okay. So
it's that sensitive, why doesn't it apply to the box of radiation?
Yeah, because there you've got, you have to study the size of the corrections and see whether it matters. Okay, but yeah, no, I mean, so this, as I said, this part of the talk, I have not dotted all the I's and crossed the T's. It's just something that I don't understand, and I want to share my non-understanding. Now I want to tell you something that I do understand. Okay. So here's a mathematical problem. So I'm going to study a product Hilbert space, HB times HA. Okay, not B tilde star. And so B you should think of as the zone, just for intuition. But from now on, I'm just going to just proceed using the symbols. The question I want to know is I have a random subspace HS. Okay, and then what I want to understand is so clearly if HS is the whole space, then there will be all sorts, any state, that what I want to know is how likely is it that there are weird states in HS, where weird means not that B is not maximally entangled with A. Okay, that's a quantitative question, and I can study it as a function of the size of HS. So clearly, if HS is the whole space, then it will have weird states because it has all the states. But the what? Yes, absolutely. Just to be a little bit more concrete, so whenever I write absolute value, I always mean dimensionality. So I will define the dimensionality of the full space divided by the dimensionality of S to be 2 to the delta n. Okay, so delta n is the number of additional qubits that you need to get the full product space on top of just this subspace. Okay, and I'm going to study things as a function of delta n. Okay. And just to say it again, I choose the subspace randomly, so we're all clear about the problem. I pick the subspace randomly in this product space, and I ask what's the probability that I can find any pure state in the subspace, which eventually I'm going to say deviates from thermality by some amount which is more than epsilon, where we can choose epsilon. And I'm going to tell you the answer to this question. Okay, so to answer that question, I need some tools which are familiar to some people, certainly to anyone who hangs out with Patrick, but may not be familiar to everyone, so I'm going to review them. Okay, so the first idea is that when you have, say you have two density matrices, you want to decide how close are they? Are they the same density matrix from the point of view of doing quantum mechanical experiments? So the way that you check is by using what's called the trace norm. So you compute the trace norm of rho 1 minus rho 2, and you write a 1 here. So this means the L1 norm. This is defined as the trace of the square root of rho 1 minus rho 2. Well, I write absolute value squared. It means this times its dagger. Okay, they're Hermitian operators, so I could just write them as squared. You should think of this as the sum of the absolute values of the eigenvalues. Okay, that's what this means. Okay, and then the statement is that if this is less than epsilon, then all probabilities, experimental probabilities from these two density matrices agree to within accuracy epsilon. Okay, this is how you distinguish quantum states. Now, this norm, so this is the good norm, but it's harder to work with. So the norm, so I have to define another norm for the purpose of doing calculations, which is the 2 norm, or the Hilbert space norm. So of course, the way this works is you just exchange the square root in the trace. So it's the square root of the trace of rho 1 minus rho 2 squared. Okay. So this is the square root of the sums of the squares of the eigenvalues. Okay, so these are not equal, but in fact, it's in general true that the L1 norm is always bounded above by the square root of the dimensionality times the 2 norm. Okay, so this is just so we can, so it can't, I mean, if the 2 norm is small, then the 1 norm can't be too much bigger. Okay, just the dimensionality is the only thing. Okay.
Can you just write the formula for those in terms of eigenvalues?
Okay. This is the well. Okay. Lambda is an eigenvalue of rho 1 minus rho 2. Okay. Yeah, of this. Yeah, it just an operator goes in here. I wrote a difference of operators because I was using it to distinguish things, but you can do this for any operator. This is the sum of the absolute values of the eigenvalues. Oh, is it? All right. Thanks, Scott. Okay, that might put a 4 in various other equations that appear. I thought that's a convention. Can I just define it?
Well, if you want it to have a maximum of 1, then
Oh, but I think with this definition, it's just there's no half with this definition, right? Yeah. I think there's no half. Yeah. Okay, this one is the square root of lambda I squared. Okay, where these are the eigenvalues of the thing that appears in there. Okay. Okay, so that's fact number 1 or definition number 1 that I need. Yeah. Yeah, so we're going to be careful about that. My advisor didn't teach me that badly. Okay, so the next thing I need are what are called epsilon nets. Okay, so when I argue about, it's very convenient to discretize Hilbert space because I'm going to be wanting to compute probabilities that states have various properties, and it's inconvenient to do that, treating Hilbert space continuously. So an epsilon net is a discretization of Hilbert space so you take a Hilbert space and you break it up into a sort of lattice set of states where you're promised that essentially that you break it up into balls in this 1 norm, and then you pick 1 state out of each ball. Okay, so roughly the epsilon net is sort of the size of the epsilon net is the number of states in Hilbert space. Okay, so how many are there as a function of dimensionality? Well, roughly you know that a Hilbert space of dimension d is really, I guess, CPD minus 1. I never remember the minus 1. But you take the sphere and then you quotient by the phase. So then the number of balls grows to some power of the dimensionality. And so indeed the number of states in the epsilon net is something like 1 over epsilon. So that's the radius of each ball is epsilon, but then we get a 2d minus 2 from the dimensionality of CPD minus 1, okay, or CPD. I don't know. I need Ed Whitten to explain that to me. Okay, so now good. So this is the number of states in Hilbert space. So that's ingredient number 2. Any Hilbert space I can discretize into this many states.
So you have something with factorials because the volume of the sphere should be relevant?
It's subleading. Yeah, no, there are various omega. You need the volume of CPD in there, but the contribution in exponent is logarithmic.
So you're basically crushing the sphere by 2.
Yeah, but it's to leading order. It's correct. I mean, the first time you derive this, you work out the integrals on. You do it correctly, including the prefactor, and you find that this is correct.
Assume the cubical sphere.
Fine. Yeah. Sure. Yeah. No, but it's okay. I mean, it's subleading. It really is subleading. I promise. Okay. So that's tool number 2 that I need. And so, sorry, I'm building all the tools first, so this may seem dry, but trust me, it'll be much more efficient once we start. Okay, and then finally, I need unitary integrals. Okay, so this is something which I did learn from my advisor. So the key thing here is the idea of the typical state in Hilbert space. So the way you make a typical state is that you just pick some state, doesn't matter what, I'll call it psi naught, and then you act on it with a unitary transformation, where the unitary transformation is pulled from the Haar measure on the unitary group. And that defines a probability measure on the space of states in Hilbert space, where you can talk about typical states. So then and then it's very convenient now, you can write down various quantities, and I will in a minute, and then you can average over the unitary group. So when you do that, the thing you invariably run into is things like, you have some integral, and then you have some polynomial, say here, so I don't know, u dagger, u, with dangling indices. And then you can do these integrals and write them in terms of tensors on the other side, and then the results are known exactly, and you can compute them in the large n limit. I won't do it explicitly, but it'll go on in the background, so I just don't want anyone to miss it when I do this. Okay. So that's it for the tools. Okay, so now I'll prove some theorems. I think I'll go into the discussion period since we had some discussion already. So first, theorem 1, or really question 1, is, so now in this setup, remember, we've got the product Hilbert space, and we've got a delta n. What's the probability that any state in the subspace S is a product state? So this is sort of the most weird. So first I'll do the most weird because it's easier, and then we'll look at smaller deviations. Good. I don't want to write it because writing is slow. But what is the probability that in this subspace there is at least one state which is a product state?
Actually, I'm confused about the B and A division versus the subspace. Is there anything you're assuming about the subspace that it contains A or B or something?
The Hilbert space factorizes is a tensor product of HB times HA. The subspace is just some subspace chosen in that Hilbert space randomly.
And you're asking about just the chance that I can find your state in that subspace?
Well, I want to find it. So I first choose a random subspace. Random in the sense of what I said here, using the Haar measure. And then I ask, what's the probability that in that subspace there is a product state? If the subspace is smaller,
with respect to the AB division.
To the AB division, yeah.
So for example, this is not very random, but if the subspace were a subspace of HB.
What? No, that doesn't make sense. Subspaces, this is a constant problem in this conference. The subspaces are not subfactors, and they're also not operators, and sometimes they all get smeared together. And right. Right. Okay. So here we go. So this is very easy. So the probability of finding a product is very easy to write. It's the number of states in the subspace. So because we get to try each time in the subspace, and then it's the ratio of states in the whole Hilbert space which are products. So that's the number of states in A times the number of states in B divided by the number of states in AB. Okay? So this is the fraction of, so now I'm using the epsilon net. So I discretize the whole Hilbert space HB times HA. Okay. Then I ask what fraction of those states are product states. Well, so this is the number of product states. I guess I get to pick a state in A and I get to pick a state in B. This is the total number of states. So this is the ratio of states which are product states. Now I have a subspace, and so I just want to know that I only need one of them to be a product state. So I just get to multiply by the number of states in the subspace. Okay. So and now we can compute this using this formula.
So if you didn't discretize, this would be equivalent to asking for a state which is within epsilon.
That's correct. That's correct. So epsilon is going to appear here. Yeah.
You really mean close to really?
Yeah, I mean within distance epsilon of a product state. Yes. It would, of course, it would be 0. Yeah, it's measure 0. Yeah, of course it would be 0.
By which norm?
By the one norm. Yeah, the epsilon net is defined with respect to the one norm, which is the correct norm. Okay. Okay, good. Now I can compute this using this formula. Smashing. Okay, and the answer is 1 over epsilon squared. Okay, so to save time, I'll spare you a little bit of high school algebra. Okay. What? Well, that's the point that's about to appear. So of course, so these can be neglected, of course, because I'm assuming that these guys have some sort of non-trivial size. And the point here is, okay, say delta n is 1. Okay, this is ridiculously small. This is doubly exponentially small in the size of the whole system, which means, not a snowball's chance in hell. Okay. I should comment, I think. Sigma? Where's? No sigma. There's epsilon squared. Yeah, sorry. I took the 2. There was a 2 here, and I moved the 2 down in here. I apologize. Okay. Yeah, so right. As long as it's 1, then there aren't any product states. Good. But of course, product states are not, product states are fine for making their argument, but they don't need product states. They only need states which differ appreciably from thermality. So now I need to strengthen this argument to deal with that case. Okay? Yeah, I should comment, I guess. So I was talking to Adam about this yesterday, and he showed me his note from March for when he did this calculation too. Which is also when I did it for Raphael and CERN. I don't know if this is the correct place to make this comment, but since you just referenced our argument, I think we also argued that delta n is small and not order 1. Did you? I don't know. I wasn't sure if you argued that. That was what we argued. Can we postpone trying to decide the size of delta n? I want to tell you the theorems, and then we can try and pick the size of delta n.
I don't think you've yet explained the relevance to our argument, so that's right. So we should assume that's coming in the future. Well,
the claim, I think I suggested, but I'll try and say it more clearly at the end. Okay. The dimension of S is absolute value of S, but I exchanged it for delta n. So I'm parameterizing it by the difference in qubits. Okay. Okay, good. So now question 2. So question 2 is, what's the probability that in the subspace S there is a state which differs in the one norm from where rho B, so the reduced density matrix on B, differs from the identity density matrix on B in the one norm by more than epsilon. Okay. So this is now the question I want to quantify. What's the probability that I can find a state in the subspace where there's any observable deviation from thermality, limited by accuracy epsilon? Okay. Yeah, I'm assuming that B is smaller than A, although I haven't actually used it anywhere yet.
Do you want to use delta since you already use it?
I mean, the answer will, of course, the answer will, typically they'll be close only if B is less than A, but I haven't used it yet. Sorry, was there another?
Oh, I was just going to say, you already used epsilon. Do you want delta?
Yeah, I think, can you forgive me and let me call it epsilon? Yeah, it kind of makes sense to sort of use the same accuracy for the discretization and for the, okay. So, okay, good. In order to do this, I need to write psi AB as some u acting on psi naught. Okay, and then I'll define delta rho B indeed to be rho b minus IB over that. Okay. The identity matrix on the subfactor B. It's the unit operator on the subfactor B. Yeah. So right, good. This density matrix acts just on HB. I traced out HA. Okay. And for the record, the thing that I said before tells you that the one norm of delta rho B is less than or equal to the square root of the dimensionality of B times the 2 norm of delta rho B. Okay, that was just what I said before. So good. So now we can proceed. So by using this unitary integral technology to understand this probability. Yeah, was there a question?
I didn't understand the definition of what you're trying to do. So
I want to compute the probability. So I choose, again, I have B times A. I choose a random subspace. And then I want to know what's the probability that in that subspace I can find a state where rho B differs from this by more than epsilon. Okay? I'm going to try and argue that this is small, and then therefore that all the states in the subspace have thermal rho B. Okay, that's going to be the goal here. Sorry, this is much more technical than the other talks. But, okay, so good. So using the unitary integral technology, we can fairly easily show that the integral of the 2 norm squared of delta rho B, which you can reinterpret as, of course, the integral of the trace of rho B squared, is equal to 1 over the size of A plus things that are smaller. Okay, so there I use that unitary integral that I talked about before. So then, in particular, using this inequality, you can show that, well, let's see. So now I want to turn this into, so this is to find out typically what's the size of this. So the square of the typical size of the 1 norm is less than or equal to, by Jensen's inequality, to the integral of the square of the 1 norm. Okay, so sorry if you don't know Jensen's inequality. And then now I can use this to relate this to the 2 norm, and therefore to the calculation I just did, which tells us that this is less than B over A. Okay, so this is one actually. So already this is one statement of Page's theorem. It says that if A is bigger than B, then typically the deviation from thermality is bounded by something which is ridiculously small. Okay, so that's, now you can actually, just as a side comment, you can turn this explicitly into Page's formulation of the theorem. Yeah. No, they're singly exponential. Singly. So these are Hilbert space dimensions. These are. Yeah. Each is 2 to the number of qubits. Okay. Yeah. Good. So it's pretty. I mean, maybe I won't write it out just because I don't want to take forever. But so if you take these results and then you write out the entanglement entropy for B, and you compute it for the density matrix rho B equals this plus that, and you Taylor expand in this, then Page's theorem drops immediately. So you get this thing that S is the log of B minus B over 2A. Okay, homework, 2-minute homework problem. Okay, so yes, this is fun technology. Okay, so this tells us that on average, the states are very close to thermal, but that's not quite what I wanted. This question is a question about the tail of the distribution. It's saying, can I, okay, typically this will be small, but can I find one where it happens to not be small? Okay, so okay, now here's how you deal with that. So I know the variance. What I'm going to do is I'm going to imagine that the distribution for delta rho B, which is generated by the Haar measure here, is a Gaussian ensemble. Okay. You can try and justify this by the central limit theorem, but this is the one part of this which is not completely rigorous. Although I'll comment on something related to that in the end. So I'll imagine that the probability distribution for delta rho b as a matrix is proportional to e to the 1 over 2 sigma squared trace of delta rho b squared. Okay? Yeah? That sounds good. I'm a dim-witted guy, so but.
What's delta rho b?
Delta rho b is this. It's the deviation. Yeah. I think that it's pretty. I mean, by some sort of central limit argument, it seems hard to believe that it wouldn't be this. But I'm actually. Well, I'll make a comment about this at the end, though. So this is going to end up being rigorous. But let me present it this way because this is the straightforward way to understand it. Okay, good. So and then now this sigma is a parameter, so I have to choose the sigma to fit this. So this tells you the variance, so then that tells you sigma. Okay. So with that, so now given that, okay, now this just becomes some fact about Gaussian integrals. You can essentially what you want to do is turn this into a chi-squared distribution by integrating out all of the spherical directions. And the result is that the probability that the one norm, delta rho b, 1, is greater than epsilon, scales like e to the minus epsilon squared over 2 times a times b. Okay? Okay, so I mean, what else could it be, right? But it's good to have an argument. Good. So now we're almost done. So now we know the probability that any particular state deviates by the amount that we want. Now we get to multiply by the size of the epsilon net to again now find the probability that we can find any state. Okay. But the point now is that this is still. So I mean, this a times b is the same a times b that we found before. So maybe I'll write it up here. That was a bad idea. Okay. So indeed now if you throw it all together, multiplying by the epsilon net, the probability is this. Okay, so now there's an epsilon squared that wasn't there before. And now 1 minus 2 to the minus delta n over epsilon squared times some constant that we don't care about. Okay. So again, we find that now, well, delta n, it can't quite be 1 because there's this epsilon sitting here. But it doesn't have to be very big. I mean, in particular, if we imagine that we're allowing limited precision, we say, I don't know, say we can measure things to 1 billion accuracy. I mean, this exponent is pretty helpful. And so delta n doesn't need to be very large before you can beat this down. And then you get this ridiculously large factor here, which tells you that there's no chance of finding states which deviate from thermality essentially at all.
So again, in our paper, I don't know what A and B are because we were concerned with the whole Hilbert space of the conformal field theory. So I'm still not sure where this is going in terms of our ability to use a basis.
Yeah. So good. So B is you should think of B as being your mode. Okay? Mm-hmm. And then A times B is the closest approximation to the microcanonical ensemble that factorizes. Okay? And then that defines delta n, and that's a technical question to decide what's the delta n there.
Good. The subspace is the microcanonical ensemble.
Yeah, the subspace is the microcanonical ensemble.
Good.
Okay?
Yeah.
So what we've learned here is that if delta n is essentially order 1, then the microcanonical ensemble doesn't have any bad states.
So if our operator B were instead hit on both sides with a projection operator that kept you within that band of energies, it would be exactly diagonalizable.
Let's see.
Just by construction.
Yeah, that sounds correct.
Right, good. And so we simply have to show that operator would have an order 1 commutator with n sub a.
Yeah, let's see. Yeah, I guess you needed to still have the interpretation that you want, though, right? I mean, let me say what I'm imagining this allows you to do. So, well, I mean, I don't know the answers to all these questions, so I'm happy to discuss them. I mean, I think so. Yeah, good. Let me wrap up. So, the main task here, I think, is to figure out what's delta n. Okay. I mean, I sort of oscillate on this. Sometimes I think it's proportional to the entropy. Sometimes I think it's proportional to the log of the entropy. Sometimes I think it just has to do with the size of the mode and not with the size of the black hole. I really have not settled on a value for delta n. So this is a quantitative question to figure out. But I should say, but let's imagine that it's big enough that this argument works, okay, that it applies. Then I think what this would be saying is that, so you can still ask, so where are all the product states? What are all these states? Which, I mean, they're there. I'm not saying that they're not there. I'm just saying they're not immediately in this particular subspace. But then the point is that, well, once you allow them to be out of the subspace, you now have this problem where you can say that a state which looks bad from the point of view of one ensemble is really just an atypical state from the point of view of higher energy black holes. And then there's lots of room. I mean, the Hilbert space is growing enormously for you to fit in all of these these bad states in such a way that there's no value of the energy for which these are actually the typical states in the ensemble. And then, so then,
is this the right point for me to comment, or should I wait till you're done?
What? Well, let me just see. I think that was.
Can you estimate this by saying, take the Harlow-Hawking vacuum, you can prove that you consider a product state.
Mm-hmm.
With the energy. I mean, this is something that we're going to talk about vacuum,
This is how we claim to have estimated the answer. We claim to have estimated. We have a microcanonical ensemble. Okay, we're interested in states obtained by putting our number operator in a definite energy eigenstate, and by measuring the energy width of those eigenstates, we claim to have estimated the amount we have to grow our microcanonical ensemble, and we claim that the answer is you have to increase the energy by the Hawking temperature divided by a logarithmically large factor, which means that the number of bits you add to the Hilbert space, your delta n, is logarithmically small. So we agree with the conceptual point. We claim to have done an estimate of delta n in vector field theory, and we claim to have argued that it's small.
Yeah, good. So I mean, I'd like to understand that. That's not in the paper, but maybe there's some sentence which
I'll show you the
some
footnote.
roundabout way applies.
Were you the referee, by the way?
What?
Daniel, would it be okay to model this argument in terms of an ordinary system where we have black body radiation and we let one photon escape, and we ask, what is the chance that what I'm left with could still be a product state with respect to the division of the original radiation into two halves?
Maybe, I don't. I mean, it's
because I think there's no question that your argument. I mean, look, this math is correct.
Yeah.
But I have a feeling that it leads to statements about properties of microcanonical ensembles that are just not.
Yeah. I mean, good. So I'd like to understand this. I mean, I should make one comment. So there was one thing here that was a little bit non-rigorous when I pulled out the Gaussian ensemble. So I should mention. So I was talking to Douglas yesterday morning, and I mentioned I was thinking about this, and he said, "Oh yeah, I think there's some paper by Patrick that talks about these kinds of things." So Patrick, so I went and looked in Patrick's paper. So of course, indeed, he talks exactly about this, but of course, it's Patrick, so it's completely rigorous. And I should just comment that the only difference that between what I got here and what Patrick has is that you get rather than having delta n be order 1, you need it to grow like the log of the dimensionality of b. Okay. And then, so that this order of things I was throwing out left and right in this derivation. But if you're careful about them, then this is what you find. And then that doesn't have any slightly unjustified assumptions about Gaussian ensembles or anything. Sorry. But yeah, I mean, in terms of the physics, I mean, yes. So yeah, I'd love to understand better how do we decide delta n. I have not found I mean, to me, it's clear that it's not 0, and it's clear that it's sort of at most have ordered the entropy of the black hole, but then I haven't really found a convincing way to sort of pin it down better than that. Yeah.
I have a question.
Yeah.
The question has no identity.
Yeah.
It's true. Let's say it's true that these states correspond to exceptional states in higher mass black holes. Aren't these kind of mass black holes contained in the canonical ensemble of the original black hole? Aren't they part of the entropy, part of the original?
Yeah, I think they're, maybe the. Yeah, I mean the ensemble shouldn't be that different, right? I mean, you pick your temperature, and then it should be dominated by black holes with sort of the right energy, basically by the microcanonical ensemble. So, I mean, essentially, roughly what I was sort of imagining
here. The answer is, if they're in that canonical ensemble, then delta n is much less than 1, because the canonical ensemble has a sort of tiny width relative to a microcanonical ensemble.
Subspace as a scrambled subsystem will have come with 1 bit less.
If delta n is 1?
Let's say delta n is 1.
Okay.
So then that means that your subspace has effectively 1 bit less. In other words, I can think of it as a scrambled subsystem with 1 bit.
Okay. Yeah, that's right. That's the definition. Yeah.
So I think that.
Okay. All right. So that's what I know. All right, thanks. Yeah.
I just wanted to make some comment to the extent I could understand. This seems to be similar to what's happening and what I was thinking and what I was saying. It's just okay. It's just in that case, delta n seems to be entropy. I just want to connect.
So it's true. Herman and Eric wrote a paper where they wanted delta n to be exactly the entropy.
Yeah, that's why.
Yeah. So maybe you've been saying this in the papers too. Yeah. I think maybe the thing that sort of was amusing to me here is that sort of delta n really does not need to be very large. So it seems to me like there's at least potentially a lot of room for sort of edge effects with having to do with how you.
I just wanted to make connection.
Yeah. Okay. Okay.
Oh. Does this affect the calculation of entanglement entropy in field theory? So in field theory, when we calculate entanglement entropy,
I don't think so, because I mean, there you're usually you're in a particular state, right? You're in the Harlow-Hawking state or the vacuum, or however we want to think about it.
So we're in the vacuum, but normally you assume that you can trace over. Well, that's true. It's not. We're not assuming a product state, but we're assuming we are considering a product state basis to do the computation.
Yeah, so you're allowed. That's what I did here. I used a product state basis to compute everything, right? I think it's fine. That's a particular state, and that state has the properties that I say most states should have, right? So.
Maybe I can make one comment about this. One way again of thinking about these delta n's, and we call them virtual bits, and they are part of the discussion because. Before the firewall was introduced, there was a lot of discussion indeed, starting with 't Hooft, who was indeed making the same point as what's now called the new firewall argument. Namely, that if indeed you do any measurement on the outside radiation, any projection that you would do on the Hawking state would make the horizon state singular. And actually, you can use then a phase space argument in the same way exactly as was done in what's now called the new firewall argument, that the inside of the black hole would never be real from the perspective of the outside observer. That's what complementarity, one part of complementarity, that the inside of the black hole is not there if you're able to measure the Hawking radiation. So if all the bits that you would be measuring even close to the horizon are the same bits as the one that you measure asymptotically, then the new firewall argument was already there in the discussion of 't Hooft.
Well, okay.
I'm not talking to you. I'm not talking to you.
Fortunately, I am very young.
Let me finish. Let me finish this.
Historical.
Let me finish this. So the answer that people were always giving to 't Hooft was saying, "Oh, you're doing it wrong, because these particles that are at the horizon are not real. They're virtual. They're part of the vacuum." That was always the counter argument to what 't Hooft was saying. So for many years, when information loss was there, the fact that there were virtual particles was always the thing that was being used to argue that there was a delta n that was big. And now suddenly we're in the new post-ADS-CFT era, and then suddenly there's no such thing as virtual bits. Every bit we're supposed to be talking about is supposed to be real.
I don't
now,
know.
And then people are saying that delta n is small. So we kind of seem to have switched from one extreme to another extreme, where every bit we have to talk about has to be real. And previously, the bits that were near the horizon were virtual. So I think this is an important point of how many of these extra bits do you need in order to make this particular.
I don't want to make these up, though. I mean, I want to be in the physical Hilbert space of black
but I'm
holes.
just saying it's actually a very relevant discussion of how many of these things you need.
Okay, thanks.